Hi everybody, welcome to another episode of FP 101X. And what we're going to do today is we're going to look how to define functions in Haskell. Now, I think everybody of you that has been to college in a different town than where they grew up has had this experience, in one way or another. You leave your hometown where you grew up, you went to elementary school, you went to high school, you go off for college, and then 10 years later, you come back, and things have changed slightly, but they are also a little bit the same. And that can be a little bit disorientating because, in your memory, things, were like they were, but in reality, they have changed slightly. Well, you will get the same experience when you look at Haskell. Haskell looks very familiar to other programming languages, but it kind of differs in subtle ways. And the goal of this lecture is to walk through some of the syntax of Haskell function definition and expressions and compare and contrast these with how you do these things in other programming languages. And once you're aware of these differences, it will be fairly easy to adapt to them. But there are some things where Haskell is definitely a little bit different than what most people are used to in Java or in PHP or whatever your favorite language is. So the first thing is conditional expressions. Every language has conditional expressions, and often there's a difference between conditional statements that are written using if then else, and conditional expressions, ternary expressions, that are written with question mark, colon. Other languages do have if then else for expressions as well, for example in Scala, but if you're using C# or Java, there's the conditional statements, and then for conditional expressions, there's different syntax. Well, in Haskell, since there's no statements, when you want to write a conditional, you write if then else. Okay, so in this case, we're defining a function that takes an integer and returns another integer, and it's defined, this is the absolute value, so it takes a value and says that if that value is greater than 0, then you return n, else you return minus n, you negate the value. So here you see that we're using the familiar if then else as an expression form. Of course, since it's just an expression, they can be nested as well. And since conditionals are expressions, you always have to have a then and an else part. All right? So in this case, you can define the sign of a number. So if n is less than 0, it's -1. If n is 0, then the sign is 0. And else n is greater than 0, then the sign is 1. All right? So you always have to have both a then and an else branch, just like in ternary expressions. Now, because Haskell people like brevity, they often don't use conditional expressions, but they use so-called guarded equations. And a guarded equation captures a common pattern where a function starts with a conditional. So if the right-hand side of a function definition immediately has a conditional, it's often nicer to use this form with guarded equations. So you write your function definition to your left-hand side, and then you write your conditions here. So the absolute value of n is n when n is greater than equal or 0, or it's minus n otherwise. And otherwise is just another alias for false. Now let's go back to the definition here. of the absolute value using a conditional. And here you see what I said, is that this is a function that is defined immediately using a conditional, and Haskell people prefer to write it like this. And now you see that the right-hand side is simpler and the cases are more distinguished. You can kind of easily reason about this. If it's greater than 0, if it's less than 0. And the other function, especially when you have nested conditionals, this becomes even more worthwhile. So in order to define the sign of a number, if it's less than 0, -1. If it's equal to 0, 0, and otherwise it's 1. So here you see the kind of mathematical heritage of Haskell, where we like to write things in a very concise way. And these guarded equations are something that are very idiomatic Haskell. So typically you don't write if then else, you write these guarded equations. Another thing that is very heavily used in Haskell and that few contemporary languages have is pattern matching. Scala, for example, has pattern matching, but there you have to use a case statement to do the pattern matching. C# will get pattern matching. It uses the switch statement. But in Haskell, you can use pattern matching directly to when you define functions. So for example, when we want to define negation, function from bool to bool, we can define it with pattern matching directly. So we can say not of false equals true, and not of true equals false. So that is a very, very concise definition of negation. Let's look at another example. Say that we want to define AND of two booleans. So it takes a function from bool to bool to bool. And we just write down the truth table for AND. So this is kind of exactly how if you look up the definition of AND in any book on digital logic, you will see the same truth table here. So we can write that down. But if you look at all of this, you see that it can be written even more compactly. Because the only case where this thing is true is when both arguments here are true. Okay? And in all other cases, it's false. So you can take these 4 cases here and collapse them down to these 2. True and true equals true. And otherwise, whatever and whatever equals false. And this underscore here is used very, very often in Haskell. And it means this is a variable that I don't care about. It's just used as a placeholder when doing pattern matching. Okay? Now, if you look at this definition, it will evaluate both arguments in order to do this match, because we are putting a pattern on both sides of the AND. Haskell people are very sensitive to this, because Haskell is a lazy language, and you want to do as little evaluation as possible in order to find the answer to this function call. All right? So a nicer definition, according to like a Haskell idiom, is the following. If it's true, then true and something is the same as B. And if false and whatever is false. So let's see if this is true. True and true equals true. True and false equals false. So true and whatever is there is whatever was there. And if it's false on the left-hand side, it doesn't matter what's here on the right-hand side, it's always false. So this is actually the kind of the most optimal definition of AND, because it only evaluates the first argument as necessary. Now in Haskell, patterns are matched in order. So they're matched top to bottom, left to right, or left to right, top to bottom, if I'm really precise. And so the compiler does not try to rearrange the patterns necessarily to make them more optimal, because the order is important, and you can intermix pattern matching with guarded equations. So the easiest thing to think about is that patterns are always matched left to right, top to bottom. You cannot repeat variables. For example, you cannot say B and B equals B and assume that this is implicitly doing equality over B. Okay, so all the variables inside a pattern must be unique. One thing that we have seen, we have written lists using these square brackets, and these square brackets really are just syntactic sugar for writing the list using explicit, cons, and empty list. All right? So when a list appears in a constant list appears someplace, it will mean this. But inside pattern matching, we often have to write lists in this form. So for example, when we want to define the head of a list, we define it using pattern matching as follows, and we write the list in cons head or in head tail form. Let's call it like that. So the head of a list with head X and tail I don't care is the head, and the tail of a list with a head that I don't care about and tail axis is axis. Right? So again, very concise definitions. And just for fun, let's look at the types. Tail takes a list, and since the tail of a list is a list, the type is list to list. Head takes a list, but the value of the head is the element type of the list, so it's A. So this thing goes from list of A to A. Now, of course, these are not total functions because head and tail are not defined on the empty list. So when I apply head to the empty list, there's no pattern that matches, and so what you will get is you will get an error, and the same for tail. Another way to say that is that a pattern like this, x cons x's, only matches a non-empty list. So if you call head with the empty list, this pattern here doesn't match because it's not of the form x cons anything. Okay? So when you see head of empty list, there's no case that matches, you get an error. The other thing is that you have to parenthesize these list patterns because remember, application binds strongest, so this would mean head of x cons, anything. So you have to put parens in these patterns to make it work. All right, that was our first part of defining function in Haskell. See you after the break.